Good day, class. Hope everyone is keeping safe and warm. Now, the school has directed instructors to give students something to do for instructional time when classes are canceled due to weather. And so, what I'm going to do today is record kind of an audio version of the information that you would need to be able to begin the next assignment for the class. It's already uploaded, and I'm just going to go through out loud all the information that I do think that you need to get started. And so the official assignment for the day would be to listen to this and begin taking a look at that homework. When we get back, we'll go over it and then also talk about some ways to work it in Excel. But the official instructions for the day are to listen to this and begin taking a look at that assignment. That assignment, if we go to the Dropbox, is Homework 5, Systems of Linear Equations. And the information that we're going to be accessing is in 5 Systems of Equations and Inequalities. And I'm going to be following along with the notes here in Algebra and Trig, Chapter 11, Systems of Equations and Inequalities. And so that's the first link here. And I'll be skipping through some of these pages in this particular document just to get through the main points that I want you to be able to take away so that you can get started on the work. The document begins on page 1027. I'll be skipping around and just mentioning what page I'm on as I'm going, in case you want to follow and read along on your own. And I'm going to begin looking at the next page, 1028. Systems of linear equations. The main keyword there is systems, because we've worked with linear equations before. Linear equations are equations of straight lines, slope-intercept form, y equals mx plus b type of equations. Now, we've mostly been looking at single equations at a time, or possibly graphing two equations and finding where they cross. And this is a direct continuation of that. What a system of linear equations means is a single equation by itself is just that, a single equation. But two equations together, like when we would graph two, that is a system of linear equations. A system is something with more than one part. So like your nervous system has multiple parts, like your nerves and your brain and this, that, and the other. So systems have more than one part. Therefore, a system of linear equations is a combination of multiple equations that we will look at and try to solve together at once. Now, again, we've done something like that before. We've graphed two equations together to try to see where they cross, and that is essentially what one does when solving a system of linear equations. Here we've got two equations. They aren't in slope-intercept form right now. Don't let that distract you. But we've got two equations here. We could graph them. And each one by themselves doesn't really have a solution. Each one by itself has two unknowns, both x and y. And if you were to graph these, you'd get straight lines, and every single point on those straight lines is a valid answer to the question of what values make this equation make sense. But when you have a system of linear equations, then the question becomes, you have your two separate lines, and the solution to that system of linear equations is, where do those lines cross? I'm going to scroll down here a little bit to show an actual image of lines crossing on page 1029, excuse me. And so here we've got two lines crossing. Each one has their own equation. And this one spot where they cross is the solution to that system of equations, meaning that this set of coordinates is the one spot that both lines share. It's the one spot, the one pair of x's and y's, that when plugged into both equations will give you a true answer. I'm going to go back up to these two equations up here. 2x plus y equals 15 and 3x minus y equals 5. These are two separate equations, and when graphed, to kind of give the game away, they will cross at coordinates 4, 7. X equals 4, y equals 7. And that is the one set of coordinates that when plugged into both equations will give you a true response. So the first equation, 2x plus y equals 15, if you plug in 4 for x and 7 for y, you will get an answer of 15. And for the second equation, 3x minus y equals 5, if you plug in 4 and 7 into that, you will get 5, which is a true response. You want one side to equal the other. And so even though each equation gave you a different answer, the same set of coordinates worked for both, and that makes it that one set of coordinates, 4, 7, makes it a solution to both. And it's the one solution that causes them both to cross and both to have the same a true response. And so that's largely what we're going to be doing in this lesson. And remember, we're working with systems of equations in general, is trying to figure out different ways to determine where these graphs would cross, where these lines and eventually non-lines are going to cross, and therefore what is the solution that solves every equation in the system with a true answer. Now, technically speaking, not every pair of lines you graph are going to cross. Usually they will cross exactly once, and that one spot will be the one solution. We did talk about what happens if you graph parallel lines, in which case they will simply never cross. We call that an inconsistent system. They will never cross, they will never share a solution, so you can't really solve that system of equations. There's a third candidate where if you just graph the same line twice, that's called a dependent system, where the lines just are always touching, and therefore there's infinitely many solutions. These two situations are going to be pretty rare. Inconsistent will come up occasionally, so you will have to keep in mind that sometimes lines just don't cross. But by and large, we're going to be finding single solutions to the question of where do these lines cross, what is the solution to this system of equations. There's a couple of different ways to solve them. There's a couple of different types of questions that you'll be prompted to look at in the assignment for this particular lesson. First up is confirming whether or not a provided solution is an answer, is a solution to a system of equations. So here we've got two equations, and we've been asked to determine if the ordered pair 5, 1 is a solution to this system of equations. In which case, you would plug 5 in for x and 1 in for y into both and see if you get two true responses. For the first equation, the left side needs to equal 8 for that to be true. So you plug in 5 and you plug in 1. X is going to be 5, y is going to be 1, so 5 plus 3 times 1 does equal 8. So that means that 5, 1 is a point on this first line, and you get a true response for it. For the second equation, we will plug in 2 for x and 1 for y again. And so now we need, well, this equation's already got y on one side, so we need the left side to become 1, basically, for this one to be true, and that does in fact happen. So 2 times 5 minus 9 equals 1, that is true. So plugging these numbers into both equations gave us a true response. Therefore, this ordered pair is a spot where the lines will cross, and therefore it is considered a solution to this particular system of equations. So sometimes you'll just be asked, hey, here's an ordered pair. This is how you test your system of equations to see if that ordered pair is a solution. Sometimes you'll just be asked to check by graphing, in which case you would want to graph your two equations to see where they cross. Now, you won't always be provided your equations in slope-intercept form. Neither of these are in slope-intercept form, and so they have to be rearranged first before you can graph them. So do note that. And if you're given an equation like 2x plus y equals -8, you would have to rearrange it a little bit, subtract 2x over to the other side to turn it into slope-intercept form before you could graph it using the usual slope-intercept rules. But if asked to check the solution to a system of equations by graphing, you rearrange them, graph them, see where they cross, if they cross, and where they cross is going to be the solution. These two do happen to cross at coordinates -3, -2, so that is the solution to this system of equations. Now, that's not the only way to solve systems of equations. We're going to explore lots of different ways, both assisted by technology and today not so assisted by technology. Today we're kind of laying the groundwork for how these systems can be solved on paper so that we can then better understand and appreciate how to do it quickly using Excel and later MATLAB. The first way I will now describe solving a system of equations is using substitution. We've done this a little bit. I'm scrolling now down to page 1032 if you're following along. And so we're going to solve this next one using substitution. And that means basically plugging one equation into the other to try to cancel out one of the unknowns and make that second equation solvable. To give an example, let's take a look at this system of equations here. We got negative 2x plus y equals negative 5, and 2x minus y equals 1. We're going to solve this one via substitution. And to solve via substitution, you want to take one of your two equations and rearrange it so that it's solved for one of those variables. Here we've already got the first of the two equations rearranged and solved for y. Just add x to both sides, and we turn it into y equals x minus 5. Now, to solve by substitution, now that we have the equation in terms of y, the equation says y is equal to x minus 5. That means technically anywhere you see a y in this system of equations, you can replace that y with x minus 5, and it's completely legal to do so. You can replace any y you see with an x minus 5, and that's exactly what we're going to do. If we take the second equation, the one we didn't just rearrange and solve, 2x minus 5 equals 1, 2x minus 5y equals 1. The y in that equation is equal to x minus 5. And so to solve something by substitution, you're going to take that solved equation and plug it in, substitute it into the second one. So 2x minus 5y equals 1 will become 2x minus 5, open parentheses, x minus 5, close parentheses, equals 1. We take the first equation and we're plugging it into the second. The reason we're doing that is because if you just try to solve the second equation by itself, you'll never get an answer for x or y because you don't know what either of them are. But using this tactic, in solving for y and then replacing y in the second equation with x minus 5, the second equation no longer has a y in it. Now it just has multiple x's in it. And yes, that x is in more than one place, but that does now make the solution, this equation, solvable. You can now turn this into just the statement x equals 8 with enough steps in algebra. And that is an answer. We have determined that the x coordinate that solves this system of equations has to be 8. Sorry, I misspoke. Has to be 8. X equals 8. So wherever these two lines cross, the x coordinate is 8. And once you have that coordinate, finding the y coordinate is a lot easier, because now that you know what x is, again, anytime you see an x in this system of equations, you can replace it with an 8. So that's just what we're going to do. We're going to replace x in the first equation with an 8, and then that equation no longer has an x in it anymore. We can then solve it for y, and that y ends up being 3. So we found x equals 8, y equals 3. Therefore, the solution to this system of equations is the coordinate 8, 3. And you can check your work by graphing them to make sure that that is the spot where they cross. You can check your work by plugging 8 and 3 in for x and y in both equations and make sure that you get true responses. So that is solving by substitution. There's one more method that I wanted to cover. We'll talk about how it's applied to systems of 2 equations, and then we're going to talk about how to apply it to a system of 3 equations at a time. And that is the addition method. If you weren't aware, you can technically add 2 whole equations together. You can take one equation and add it to another one. What do I mean by that? Let's take a look at this next system of equations. X plus 2y equals negative 1, and negative x plus y equals 3. Now what we're going to do is, rather than plug one equation into the other, we are going to take these 2 equations and just add them together completely. And when you add 2 equations together, you're going to add the entire left side together to create the new left side of your combined equation, and you're going to add the right sides together to create the new combined right side of your equation. And the reason we're going to try to do that for this pair of equations specifically is, notice the x's here are opposite one another. We have a positive x in one and a negative x in the other. And if you add x to negative x, so x plus negative x, well, that's just going to cancel out. X minus x basically is 0. So when you add together everything on the left side here, x plus 2y minus x plus y, the x's are going to cancel out. X minus x is 0, and 2y plus y is 3y. Then on the right side, negative 1 plus 3 is 2. So we have combined our 2 equations here to create this third equation, 3y equals 2. And the reason we did that is we now have a third equation with only one variable in it. It's just 3y equals 2. There's no x's anymore. We added the two equations together in such a way that x is gone. And that now makes this third combo equation solvable. We can solve this for y. You can solve it to get y equals 2/3. And now that we know one of the two letters, we know y equals 2/3, well, we can plug y equals 2/3 into either of the previous equations to solve for x. And so negative x plus y equals 3. If y equals 2/3, x would have to be negative 7/3 for that equation to be true. And therefore, the solution to this system of equations is x equals negative 7/3 and y equals 2/3. And you can check your work by plugging those into each equation or by graphing the two lines to see where they cross. And so the solving a system of equations by addition exists to try to strategically cancel terms from one equation out. One of the terms, you want to cancel out one of the terms entirely so that the third equation you create only has one in it for you to then need to solve. And sometimes this method is going to be easier than others. In this particular case, these two equations add together very neatly, very cleanly, by which I mean there's already one term in each that when added together normally is going to cancel out. X plus negative x cancels out, and that's why we got just 3y equals 2. It won't always be so neat when you have to use, or when you're asked to use the addition method. For example, if you were asked to use the addition method to solve this system of equations, 3x plus 5y equals negative 11, and then the second one, x minus 2y equals 11. If you just added these together as they are, nothing would cancel out. 3x plus x is 4x, 5y minus 2y is 3y. None of those cancel out. If you added them together, you'd still have an equation with an x and a y in it. So if you were tasked with solving this system of equations using the addition method, you would want to take one of your two equations, possibly both, and multiply it by a number to make sure that when they're added together, one of the letters does cancel out completely. In this case, what the book recommends is taking the second equation here, since the x is by itself, you ask yourself, what do I need to multiply this x by so that when it adds to 3x, it just cancels out? In that case, 3x minus 3x would be 0. And to turn this x into minus 3x, we'd have to multiply it by negative 3. And you're allowed to do that. You're allowed to multiply this x by negative 3 as long as you multiply the entire equation by negative 3. Remember, whatever you do to one side of the equation, you have to do to the other. And so if we want to just say this x is now a negative 3x, you're allowed to do that. But in order to do that, you have to multiply everything on both sides of the equation by negative 3. Which will turn the x into negative 3x, the negative 2y into positive 6y, and the 11 into negative 33. We took the entire equation and multiplied everything in it by negative 3. You're allowed to do that, multiply everything in an entire equation by a number, as long as you do that to every single term in that equation. And so now we're going to take this newly modified version of that equation and add it to the first one. Because we're still adding the two equations together. We didn't actually change the value of the second equation. We just made all the numbers negative 3 times bigger, which, again, didn't change the values. It didn't change what the equation is saying as long as you do the same thing to both sides. So we're going to take the modified version of that second equation and add it to the unmodified version of the first equation. And now, conveniently, x minus 3x is 0, so those just cancel out, leaving you with 5y plus 6y is 11y on the left side, and negative 11 minus negative 33 is negative 44 on the right side, which would let you solve for y equals negative 4. And once you have negative 4, y equals negative 4. You can plug that into one of your two original equations in order to solve for x, which in this case, if you plug negative 4 in for y into the first equation, solve for x equals 3, and the solution to this system of equations would need to be 3, negative 4. So I like the addition method. It's really great if you can just cancel something out outright wholesale by adding the equations together. It's really nice and really convenient. But sometimes you have to do a little bit of work to make that method work. It won't always be possible. It won't always go cleanly. But if you can multiply everything in one of the equations by a number so that when the equations are added, something cancels out, that is my recommendation for if you're... the homework will sometimes ask you to use one method over the other or gives you your choice of tactic for solving a system of equations. I like the addition method if it will cleanly cancel something out. Now, the last thing I want to talk about is what happens if you are confronted with a system of 3 equations. We've only been looking at a system of 2 equations so far, but this is a system of 3 equations that has 3 unknown variables in it. So these 3 equations here, the 3 unknowns scattered between all 3 of them are x, y, and z. And the strategy for solving a system of equations like this is a little bit different. Now, a system of 3 equations can still cross in one spot. And usually if that system has a solution, it's going to be the one spot where these 3 planes intersect one another. And that can happen, but exactly how to find that solution is going to be a little bit different. Now, sometimes you'll just be asked, is this ordered triple a solution to this system of equations? And this works the same as if you're given an ordered pair and asked to confirm if that is a solution to a system of equations. Right now I'm on page 1048 if you're following along. And ordered triples are just like ordered pairs. It's just there's a third letter in there for x and then y and then z. And so to check if this ordered triple is a solution to this system of 3 equations, you would plug in these values for x, y, and z into each and see if you get true responses. Now, the really tricky one is if you are given a system of 3 equations and asked to solve it via the elimination method. And this is very similar to the addition method that we explored before with a system of 2 equations. It just takes a few more steps. So here we have a system of 3 equations. And to solve them by elimination, we're going to want to add these together in different combinations to try to eliminate variables one at a time so that we can start finding what single letters are supposed to be. We're going to, say for instance, add multiple equations to each other in different combinations so that we can try to eliminate letters one at a time and figure out what those letters need to be for the solution. So note in this system of equations here, each one is numbered 1 through 3. And to use the elimination method to solve a system of 3 equations, you should start by looking at just the first 2. Well, it doesn't have to be the first 2, but in this case I'm going to recommend taking a look at the first 2 here. If we look at these first 2 equations here, very conveniently, one of them is, its x term is just x, and the second equation, its x term is minus x. So these 2 equations by themselves are a great candidate to be solved using the addition method, because if we add these 2 equations together, the x's cancel out. Now, we do that in this case because both of these equations have 3 variables in them. That doesn't actually give us anything that we can solve right away because our newly created equation still has an unknown in it. It's still got 2 letters in it. So we can't solve this one for one of those letters just yet. But hold on to this equation, because now what we're going to do is we need another equation that we can add to this one that just has y and z in it. And our original 3 equations, none of them have just y or z. They all have x, y, and z. So we need to create another equation on our own that will meet that criteria. And so the first time, we got this equation here by adding together 1 and 3. And so to continue on from there, you need to then look at a different combination of 2 of the 3 to add together to create another new equation, like this one here, that only has y and z in it. So I'm going to recommend taking a look at the first equation and the third equation. Note that for the last batch of eliminating we eliminated x. And so now we have this new equation here that only has a y and a z in it. And so we need another equation that also only has a y and a z in it. So I'm going to look at the first equation and the third equation here. And they need to be added together in such a way that their x's, their combination of x's, also cancels out again. Now, the first equation, the x term is x. The second equation, the x term is 2x. In order for these to cancel out, I would recommend turning the first equation's x term into a negative 2x. And in order to do that, you have to multiply everything in the first equation by negative 2. And so that's what's going on down here. We've got the third equation and the first equation. See the numbering there. But that first equation, everything in it has been multiplied by negative 2. Negative 2 times x is negative 2x. Negative 2 times negative 2y is positive 4y. Negative 2 times 3z is negative 6z. Negative 2 times 9 is negative 18. So this is the first equation. Just all the numbers have been multiplied by negative 2. So that when you add it together with the third equation, those x's cancel out, and now we have another new equation that isn't part of the original system that is only in terms of y and z. Only in terms of y and z. And so now we have two equations. This one should be labeled 4 right here. We have equation 4. Ignore that 3. This should say a 4. We have equation 4 that we made and equation 5 that we made that both only have a y and a z in them, meaning that when we add these two together, we can actually cancel out one of those two remaining variables, leaving us with only one variable left that we can actually solve for. So by taking the first of those two equations we made, this should be equation 4, and adding it with the second of the two that we made, equation 5, conveniently, the y's will already cancel out when added together, so we don't have to change anything about these two. When we add these together, the y's will cancel out. Y minus y is 0. 2z minus z is 1z. 3 minus 1 is 2. So by adding these two together, we now get a sixth equation. We've turned 3 equations into 6. That is just z equals 2. And therefore, the z part of the solution is z equals 2. And that means we have one of the letters. We've solved for one of the letters. And now that we know that z equals 2, we can take z equals 2 and plug it into one of our two equations that we made that is just y and z. And then that will tell you what y is equal to. And once you have what y is equal to and what z is equal to, you can plug y and z into one of the original 3 equations in order to solve for x. So if you are asked with solving a system of 3 equations via elimination, it's just the addition method. It just takes longer. Instead of adding once, you kind of have to add 3 times. There's way more equations floating around, so there's not many of those in the homework. But when asked to do so, this is what it's referencing. That is what you need to do. Now, that is all the information that you need to begin taking a look at this homework assignment here, homework 5, Systems of Linear Equations. So your official instructions are to begin taking a look at that. Begin working on that as you can. Now, when we do meet back in person, we are going to go back over this information, practice it a little bit, and then we will also work on how to speed this process up using Excel. If you have any questions about any of this information, anything that you encounter as you are listening to this information, trying out the homework, or even finishing up older assignments, please let me know, email me, and I will give you a prompt response. I'll make sure to help you out. And as a reminder, we're going to go over all of this when we meet back in person anyway. So again, let me know if you have any questions. Stay safe, stay warm. Let me know if you need anything, and please have a wonderful day.